Okay, so in the last video we were talking about Riemann sums, if I'm pronouncing that correctly, and how you can approximate the area under a curve. We came up with an equation a bit like this. This would be approximately equal to our area we were looking for, under us within certain bounds. Now, in differential calculus so far, we've been talking about derivatives, which are basically finding slopes at a single point. But finding slopes at a single point isn't possible because you need 2 points to make a line. So, what we do in differential calculus is take a slope between 2 arbitrary points and then take the limit, what it's getting to, as one point is becoming the other. What is it getting closer to? What is it slowly approaching? Alright, is there something a little bit similar that we could do here? Now, this of course is most accurate when this delta x is nearly 0. It can't be 0 because you can't find an area of a line. But when it's nearly 0, when it's almost 0, which would mean n is basically infinity. We need to find when x is infinitely small is when we'll be accurate, which would mean that our number would have to be infinity. But of course we can't usually do that, can we? Because we can't just use infinity and use 0 here, because that doesn't make any sense. We can't take the tiny one. That still doesn't make any sense. But maybe we could use a limit. So, how would we write that? Now I'm going to make some space. I think I'm going to cut off some of this graph. Just give it its arm back here, since we're not really using it anyway. So, we would take the limit. If you recall limits from previous videos, if you haven't seen those videos, you can rewatch them, or if you already know what a limit is, that's great. As delta x approaches 0, when it gets to 0, it's not there yet. We don't want it to be 0, that doesn't make any sense. Or as n gets to infinity, because we need an infinite number of those little, like, infinitesimal bits to actually get something. So we want the limit of this thing as delta x goes to 0 of this stuff. Right? The sum from x equals b to a of f of x times our delta x. Alright, now what happened when we took the limit on a slope? If you recall, we took the limit as, what was it, delta x approaches 0. Basically our delta y over our delta x. And that gave us, we could, the delta y is in terms of x, so we can simplify. But that turned up giving us dy over dx as a notation, but now it's going to make a little sense. dy is basically an infinitesimal change in y. The derivative is not exactly at one point. It's at another point in an infinitesimal distance away, which is basically at the same point. And because we're taking the limits, we get the slope at a single point. So it is the slope at the single point using limits, but we can't actually just plug them into a normal slope formula and get a slope. And we get an infinitesimal change in y over an infinitesimal change in x. That's what that means. So if delta x is getting to 0, this could be, let's just go down here. This could be equal to, let's do it kind of like what we did here. Delta x is going to be dx, which means a tiny x. It's not exactly, it's still an operator, but we can represent it as dx. Now then, when we use a summation of something as another thing goes to 0, what we're doing is taking the integral. And this is taking the area under a curve precisely. just like we take the derivative at a single point precisely. So our normal summation sign turns into another summation sign that looks a little bit like this, and this is the integral. It looks like a little squiggly s here. And that's the sum of all the f of x's times the infinitesimal x's. So this is taking an infinite sum of those. And then we can actually write bounds on this too, except that we just need to write b and a. This is just a fancier sum of an infinite number of tiny things. And in this video, I'm not going to describe how you take one of these, but I am going to show you that there is a way to take the area under a curve, and that this can be useful in all kinds of things, including making geometric proofs really, really, really easy. In the next video, I will give some ideas on as to what this is and how we can take it, but really it's just the limit as we get an infinite number of tiny little boxes to get more and more accurate. Goodbye.